like to start off by saying hello. I hope you guys can all see me. If you can't, sorry. My name's Logan. I'm part of Team 3470. We do FTC robotics. That up there is a little bit earlier version of our robot Asmanov, which we're trying to get working over there, but where you need a part that someone's going to run up and grab for us. I'd like to just start off by taking a moment talking about safety. As much as everyone hates wearing safety glasses and talking about safety, safety is one of the biggest things you should work on. You should realize when working with robotics. Robotics is one of the most fun things that I do, but you got to remember, without safety, you're not going to be around or be able to do any robotics. So, just want to preface this with safety. Now, let's get into a little bit of discussion about FTC versus FLL. What they do here is FLL, and what our challenge is FTC. We get a game every year, just like you guys. The only thing is, our field and robot are bigger. We use metal parts instead of Lego parts. We use remote controls. They look like PS3 controllers. And then we have even more engineering and math in our game, because it's for high school level. Let's talk a little bit about the magic behind our innovation and how we really get to what you see over there. We use a stage in which we first design and build a prototype. We test our prototype, make tweaks until we're happy with performance, put the design into a computer-aided design program or CAD program, and we move on to the next part, as you can see here. It's a vicious cycle, and it never stops, ever. I actually have a little picture version of this. I call it thought in motion. Now, first, we sketch things out. Often, sketching things out, you can see inherent problems that you just don't see in your mind. Then we build a prototype out of Legos most of the time. So one of our ideas was crate manipulation. We have crates that we have to be able to move around our robot. Now, someone had the idea of using a wheel system. So we built it out of Legos. We then test the design. We found out Legos didn't work. We tried this little hook mechanism, hook on chain. And it turns out that didn't work either. After we finally get something that works, we put it into a CAD program, as you can see over there. We integrate it into our robot, and we test the robot with everything integrated. And then after that, we can make slight tweaks to that, but by that time, most stuff is working pretty well. Now we talk about the fun part, software engineering. So, one of the hardest part of software engineering is it's not just sitting down and writing code like most people think it is. You just go into computer, your fingers start flying all over the keyboard. No, it's a lot more of it's an art form. You have to be able to analyze, as you see here, you got to be able to analyze the challenge that you have to come up with, analyze what's the best way to use this challenge. For example, our robot has two main driving sides. So for example, pushing the bowling ball, we have to figure out, okay, which side would be better to push the bowling ball from? Because we don't want to push the bowling ball from something that would snap off and break. So we have to figure out, we have to do a lot of engineering between these two right here. And then finally it all comes to fruition here in this. This is our IDE, it's called Robot C. What an IDE is, it's like a text editor. But so basically you can just write a lot of code in it, and then it compiles it and does a lot of other stuff. Think of it like a really heavy-duty version of Notepad. Now, our robot is able to take in, analyze, and make decisions on data that comes in fractions of a second. The robot can do things like it's able to figure out, okay, which direction it's facing in the field. So it can see whether, so let's say it's trying to get a bowling ball. It can figure out which way it's positioned and try to, which would be the best way to get there. It can also determine the status of its internal mechanism. So if you'll see over there, we'll show you, it has a crate lifter that can go up and down. Now, if it's already in the down position, we try to have it go down again, it's going to burn out the motor. We have smoke and a lot of money. It's very expensive smoke. I wouldn't recommend breathing it. But so the robot is able to figure out, hey, it's in the down position, I don't want to burn out the motor, so it says, okay, I'm going to ignore what the human says to do here, and I'm not going to move it. So it's able to do stuff like this. Now as you can see over here, these are infrared lights. Now these give off a little beam that, kind of like a homing beacon, that the robot can see using an infrared sensor and go straight to it. It's pretty cool. Now one of the things we do is learn from the past. As you can see Brittany over there with the camera, wave and say hi.
Hi.
She takes pictures, and Joseph, right there, a videographer, he takes videos, and they both take pictures, videos, work on our notebook, as you can see right here. And what this does is, often we write down failures, because when failure is nothing but a springboard for future success. I'll talk more about that in a minute. But by writing down everything and documenting everything that we do, we can look back and say, hey, this wasn't the best way to do it in the future. So that's one of the things you should always do. You should always document and take notes on things. Because by taking notes, you can do things much more efficiently in the future. As you can see here, we have photos of us melting some Lexan, sketches that we keep, CAD models, and then the infamous notebook. Once again, past prototypes often turn into future inspiration for us. As you can see here, that crate lifter over there, and we'll show you that in a minute, but that crate lifter, it started out as this. It was a paddle system. And we could move the paddles up and down. But we found out that just didn't really work, because they want the paddles that would always slide off the paddles. So we took that, actually we flipped it over, and instead of paddles, we put bars on it. So things from the past that we documented, we were able to use in future designs. This is why we document everything. Here were some failed prototypes for a mechanism which is currently on our robot. These two are failed prototypes. And this is I could get the laser pointer to work. This is what finally gets on our robot. The robot's able to tell when a magnet comes in. There's hidden magnets within some of the balls. And when a magnet ball comes in, it's able to divert it onto a separate track. So by using old prototypes and using old things that we've learned, we're able to create new things that work much better. You're probably wondering who puts this all together. This is our team. Some of the best engineers of Heritage High School, all put together to create the best robot. As you can see, there are many faces in this, some repeated, but they all come together for one mission, to create the best robot that we can. Actually, here's a little video from a competition. We have a driver and two engineers talking about what the best control scheme is and different things on the robot, like they're going to be adjusting speeds and different ways, because those little bars right there, that's how the moves up and down. So like adjusting how far and how fast things go, and so they can talk and make adjustments in the pit area. And yeah, so they were testing, and that is the end of my presentation. Any questions?